Hi, everyone. Today is May 11th, and we're going to be talking about fundamental identities today, okay? And so this is the start of really the big picture of this whole unit, okay? And it's about identities, and what an identity is two things that are equivalent to each other, okay? And it's going to help us to simplify things if we take one trig function and replace it with another, okay? And as we get into this, you'll see how we can do this more and more and more, okay? So the very first thing is there's 6 reciprocal identities that I want to go over with you. And you guys actually know these, okay? All right. So one of them is this, okay? So cosecant of theta is the reciprocal of sine theta, okay? So that means when we see cosecant theta, we can replace that always with 1 over sine of theta. Okay, so these are equivalent statements. So cosecant theta is equivalent to 1 over sine theta. I'm going to start with the two most important ones. You're going to see this happen a lot, okay? And then secant theta. Okay, so secant theta is the reciprocal of cosine. So secant theta would be the same as 1 over cosine of theta. Okay, cotangent of theta, it's the same as the reciprocal of tan theta, so 1 over tan theta. We're not going to use this one very much. We use these two a lot, okay? But we're not going to use this very much. Occasionally we will use it, okay? And then we have sine theta, okay? If cosecant is the reciprocal, if cosecant theta is equivalent to 1 over sine theta, then sine theta is the equivalent of 1 over cosecant theta, okay? So 1 over cosecant theta. And same thing with this one, okay? So cosine of theta could be written as 1 over secant of theta, and then tan theta is the reciprocal of, okay, cotangent theta, so 1 over cotangent theta, okay? Now I'm going to highlight, I'm going to box, these are the two that are the most important. Of these 6, these two are the most important, okay? Because this is going to help us simplify things a lot of times, is that we can take cosecant theta and replace it with sine theta and cosine theta. Actually, all trig functions, you can somehow switch to sine thetas and cosine thetas, okay? And you can rewrite every single one of them. Now, sometimes that's not going to be beneficial, but every single trig function can be rewritten in terms of sine theta and cosine theta, okay? So here's these two, okay? So these two, cosecant theta and secant theta, are very important, okay? And I meant to start out saying this today, but this is going to be a very long lesson, okay? Usually this takes a couple days in class to do. So if you, usually I do 5 assignments during the week. If you want to break this up and do part of the notes now and then part of them later, that's okay with me, because this is going to take a little bit of time. Like I said, usually this takes a couple days, a couple class periods to work through all of these, okay? All right, let's move on to quotient identities. Okay, so the quotient identities, okay? So I've already actually done this with you guys, but I'm going to do it again, okay? One of the quotient identities is this, okay? And we're going to start with this, tan of theta. Okay, so what is tan theta? Theta is the angle that we rotate, and this is the ratio of the y coordinate over the x coordinate, okay, of that terminal side, okay? So it's y over x, okay? Now, what I can do is I can multiply by a version of 1 and change this, this ratio right here of y over x. I'm going to multiply by 1 over r over 1 over r. 1 over r over 1 over r is still 1. But what that does is it switches it, and then y times 1 over y times 1 over r is y over r over, and then x times 1 over r, because that's how you multiply fractions together, is you multiply this denominator with this denominator and this numerator with this numerator. And so this would be x over r. But what's y over r? Well, y over r, the y coordinate over the radius, is the definition of what sine theta is. So this turns out to be sine theta and over, and then x over r, that's the ratio for the angle of cosine theta, so cosine theta. So what does this mean? This means tan theta can be rewritten as sine theta over cosine theta. Now I've shown you that, okay, but now we formally did it, okay? So now we need to know this, okay? So tan theta can be replaced with sine theta over cosine theta. Okay, now from before, we know cotangent is the reciprocal of this, right? So what this would mean is that whenever we see cotangent theta, it wouldn't be sine theta over cosine theta. It would actually be cosine theta over sine theta. And you can go through a very similar argument to what we did right here. Okay, so this would be cosine theta over sine of theta. Okay, now actually, I'm going to tell you both of these are very important. Okay, now normally in normal situations, okay, we go through all these and we have a lot of them. And I gave you actually a sheet that's cardstock, and I believe I printed it on like pink paper, okay, really, really bright fluorescent pink paper, okay. And all of these identities are on that. I think it might be a couple. If you look at your packet, I think it'll be a couple away from this unit, from this lesson, that you're going to see this bright pink cardstock paper, okay? All right, so I'm going to tell you, it's very beneficial to you memorizing these. And usually I give a test where you take it like 3 times, okay? And you have to reproduce all of these trig identities, okay? So you really do need to know and commit these to memory, all these trig identities. Now, I can't test you on it this year, okay? But you really do need to commit these all to memory, okay? It'll be beneficial to you, okay? All right. So the big ones, the big ones, I'm going to zoom out a little bit. Okay. So on this first page, we've already learned 8 of them. Okay. These are 8 identities that we need to know. Okay. But really 4 of them are the most important. And it's this cosecant theta, secant theta, and then tan theta and cotangent theta down here, the 2 quotient identities. Okay. All right. So the next thing, let's turn the page. I think the next thing is Pythagorean identities. Okay. Okay, for these Pythagorean identities, okay, so here's my circle, right? I'm going to say it has radius r, okay? And then this is a point in this xy plane, so it's x and y, okay? This is the terminal side of my angle, so this would be my angle of rotation theta. And if this is x, if this has an x and a y coordinate, then this vertical leg would be the y coordinate, and the horizontal leg would be the x coordinate, right? And we have a right angle right here, okay? And these are called Pythagorean identities because they come from the Pythagorean theorem. So what we have is, we have x squared. We know from the Pythagorean theorem that x squared plus y squared equals r squared. So x squared plus y squared is equal to r squared, okay? Now, I'm going to manipulate this equation. Whatever I do to one side, I have to do to the other side. And what I'm going to do is I'm going to multiply by 1 over r squared. So 1 over r squared times x squared plus y squared is equal to 1 over r squared times r squared, okay? So if I distribute this, okay, it'd be x squared over r squared plus y squared over r squared is equal to r squared over r squared, which would just be 1. Now, exponent rules says, okay, if you're squaring the numerator and squaring the denominator, you could write this as a fraction squared. So you could write this as x over r squared plus, and this one, same thing, y over r squared, and that's equal to 1. Okay? Now, this x over r, that's the ratio of x over r. So the ratio of x over r is actually a trig ratio for angle theta, right? This one would be cosine of theta. So this becomes cosine of angle theta in parentheses squared plus what's y over r? Well, that's also a trig function. So that would be sine of theta squared is equal to 1. Now, this is what it means, but I'm going to tell you something. There's another way to write this, okay? So you're going to see it, and we put the little square in between the cosine and the theta, okay? So cosine, we write this as cosine squared theta Okay. And whenever you see this, it actually means this. Okay. So that's kind of a new notation of way to say it. Okay. But we're squaring the trig function with angle theta, right? Okay. And then plus, and then this one would be sine squared theta is equal to 1. Okay. So what this means is we can take, anytime we take cosine of angle theta and square it and add sine of angle theta and square it, it's always going to equal 1. So whenever we see this, we can replace it with 1. Now, this does not say, it does not say that cosine theta plus sine theta equals 1. That's not true. You have to square them, okay? So cosine squared theta plus sine squared theta is equal to 1. Okay, so that's going to be a very big trig or Pythagorean identity, okay? So that's a big deal, okay? So when we see cosine squared theta plus sine squared theta, that will always equal 1. Okay, now I want to do some stuff because you may see this manipulated, like stuff moved from side to side. So you need to know this one, okay? But you got to realize that you can move stuff from side to side. So in other words, okay, we can use this to figure this one out. What is 1 minus sine squared theta? That's actually a variation off this one, okay? So how do we go from here to here? Well, we'd have to move the sine squared theta over to this side, right? And then this right-hand side would be 1 minus sine squared theta. And then equals, and then this side would be cosine squared theta. So this must equal cosine squared theta, okay? So we need to know this one, but we also have to realize that if we move stuff around on this mentally, okay, we can get other variations of this, okay? Or we could have this one. What is this one? Cosine squared theta minus 1. What would that equal? Okay, well, what's that one? That's one where we have cosine squared theta here. We move the 1 over here, but then to know what it's equal, we'd have to move the sine squared theta over to the other side. So that would make this equal to negative sine squared theta. Okay, now what would this one equal? 1 plus cosine squared theta. And you should be thinking, you can't, all right? Because you can't manipulate this one to get this one, right? Because if I move, okay, here's the 1, right? If I move cosine squared theta over to the other side, it won't be 1 plus, it'd be 1 minus cosine squared theta. Okay, well, what if I move the 1 over here to this side? Well, then it'd be negative 1 plus cosine squared theta, and it wouldn't be 1 plus cosine squared theta, right? So we don't know what this one equals, okay? So you got to realize when you can't manipulate it also, okay? All right, so this is going to be, you got to know this one, okay? And I'm going to say there's going to be 3 of these Pythagorean identities you need to know, but really they all stem from knowing this one. Okay, so if you know this one, you can come up with the other 2 fairly quickly. Okay, all right, and we can move stuff from side to side. Just realize that, and you get an equivalent statement. Okay, so if this is true, these 2 must be true. Okay, both of these, because these 2 came from just moving stuff from side to side on this one. Okay. All right, so another one that we can do is I can divide both sides of this equation by the same thing, okay? So this is like a manipulation, kind of like this, okay? But it gives us a brand new one, okay? And what I'm gonna do is I'm gonna divide both sides by cosine squared theta, okay? So if I divide this left-hand side by cosine squared theta, okay? So I'm gonna get this, let's just write this, cosine squared theta plus sine squared theta. And I'm gonna divide this side by cosine squared theta. And I'm also going to divide this one by cosine squared theta. So I'm dividing both sides of this by cosine squared theta, okay? Now, if I divide this, this comes from adding 2 fractions with a common denominator of cosine squared theta. So this becomes cosine squared theta over cosine squared theta plus sine squared theta over cosine squared theta is equal to 1 over cosine squared theta. Okay, cosine squared theta over cosine squared theta. We could rewrite that as 1 plus. Now, here, I'm going to do two things at once, okay? Because these are both being squared, I could write this as one fraction being squared, and I'd have sine theta over cosine theta. And I'd be squaring that fraction of sine theta over cosine theta. But that's a quotient identity, right? Sine theta over cosine theta is tan theta. So this becomes 1 plus tan squared theta is equal to, well, this one, it could be written as 1 squared. So both of these are being squared. So like we did over here, we could write this as one fraction being squared, and we'd have 1 over cosine theta. But 1 over cosine theta is a reciprocal identity. That's secant theta. So this becomes secant squared theta, okay? And this is the second Pythagorean identity that you need to know. So 1 plus tan squared theta is equal to secant squared theta. Now, I'm going to be honest with you. I really don't have this one memorized. I know mentally that if I take this one and I divide by cosine squared theta, divide this by cosine squared theta, and divide by this one by cosine squared theta, I'd have 1 plus tan squared theta is equal to secant squared theta, okay? And so I just know how to get this one from this one, okay? So really, you just need to know this one right here, okay? Now, again, from this one, we can move stuff left to right, okay? So what is 1 minus secant squared theta? Okay, let me slide this up a little bit. So what is 1 minus secant? Could we manipulate this? Could we move stuff from side to side and get 1 minus secant squared theta? Yes, we could, right? And what it would be equivalent to is we'd have to move the tan over to the right-hand side. So that would be negative tan squared theta. Okay? What would this one be? Secant squared theta minus tan squared theta. Well, secant squared theta minus tan squared theta. Well, that would equal to 1. Okay? That would be just moving tan squared theta over to the right-hand side. Okay? How about tan squared theta minus secant squared theta? And tan squared theta minus secant squared theta, well, I'd have to move the secant squared theta over to the left-hand side, and I'd have to move to the 1 to the right-hand side, right? So that would make negative 1, okay? How about this one? Tan squared theta plus secant squared theta. There's no way to manipulate this and know what it's equivalent to, okay? Because if here's tan squared theta is positive, right? If I move secant squared theta over there, it needs to be minus, right? Okay. If I move tan squared over theta over here, then that would be secant squared theta minus tan squared theta, right? There's no way to get them to both be positive, right? So we don't know what this one equals. Okay, at least not yet. Okay, so these three right here come from manipulating this one, okay? All right, so there's one more that we can do. So if we took, okay, this one we took the cosine squared theta plus sine squared theta equal to 1, and we divided both sides by cosine squared theta, right? Well, what if we divided both sides by sine squared theta, okay? So if we divided both sides by sine squared theta, and here's where I'm gonna start doing this in my head, okay? If I divided this by sine squared theta, then I'd have cosine squared theta over sine squared theta, right? I'd have cosine squared theta over sine squared theta plus, and then I'd have sine squared theta over sine squared theta. And then that would have to equal, and then 1 over sine squared theta, right? Okay, but these are both being squared, right? So I could square the whole fraction and it'd be cosine theta over sine theta, right? Well, that is cotangent theta, and I'd have to square it, right? So I put the square right there. Sine squared theta over sine squared theta, that would be 1. So plus 1 is equal to, and then this 1 could be written as 1 squared, so you're squaring both the numerator and denominator. So that'd be 1 over sine theta, in parentheses, squared, okay? So then that would be 1 over sine theta is cosecant theta, so this would be cosecant squared theta. Now, this is the third Pythagorean identity. So whenever you see cotangent squared theta plus 1, you can replace it with cosecant squared theta, okay? Now, where does this one come from? Both of these two come from knowing this one, right? One of them comes from dividing all of them by cosine squared theta, and the other one comes from dividing everything by sine squared theta, okay? Now, are there equivalent forms of this? Like, can we move stuff around? Yes. What is cotangent squared theta equivalent to? Well, that would have to be cosecant squared theta minus 1. Okay, so that's one way, that's one we can get off of this one, right? Okay, and there's a whole bunch of others, all right? Now, I wanted to point something out, okay? Notice this is a difference of squares, right? So this is coming up. You're not going to have to do it right now. This is a difference of squares. This one's a difference of squares. Even this one's a difference of squares. And this is a difference of perfect squares, right? That means we're going to be able to factor these as a difference of squares, okay? And that's coming in future lessons, okay? So I just want to point that out right now, like you're aware of it, like, hey, that's a perfect square minus a perfect square. That's the definition of difference of squares, okay? All right, guys, so that's the Pythagorean identities, okay? There's actually 3 of them, these 3 that we boxed, okay? But honestly, again, you only need to know this one, okay? And just know I can get these 2, right? By dividing this one by cosine squared theta or dividing this one by sine squared theta, and you can get the other 2, okay? And then each one of these individually, you can move stuff around left to right, okay? All right, let's go to the next one. Okay, for this one, these are called the co-function identities, okay? I'm going to call this point down here A, and I'm going to call this one B, and this one C. And remember, this is a right triangle, right? And remember we talked about this a couple units ago when we did right triangle trigonometry, okay? If this vertice of the triangle is capital A, right? Because it's a point. So we label points with capital letters. I don't know if you realize that, okay? Or vertices, okay? So this is A. So the side that's opposite would be this vertical leg right here. We label that one lowercase a, okay? And this point or vertex is B. The side opposite is capital B, right? So the side opposite is going to be lowercase b. This vertex or angle is C, okay? Which means this side's going to be lowercase c, okay? All right, we need that for some stuff we're going to do right now, okay? So this is a 90-degree angle, right? And we know that the angles of a triangle always add up to 180 degrees, right? So that would mean that if we take 180 degrees minus 90 degrees, because one of them is already 90, these 2 angles always have to add up to 90 degrees, right? Okay, so if they add up to 90 degrees and this one's theta, this one would have to be 90 degrees minus theta. Now, I want to do this in radians instead of degrees. So instead of 90 degrees minus theta, this angle up here is equivalent to pi over 2, because pi over 2 is 90 degrees, right? To pi over 2 minus this angle theta, okay? And so now we have this angle, which is theta, and now we know this angle must be pi over 2 minus theta, okay? So I'm going to do some right triangle trig with you guys, okay, on this. So what is sine of angle theta? Okay, so sine of angle theta. So here's angle theta. Sine is the opposite over the hypotenuse, right? The opposite over the hypotenuse, because we just have a right triangle. We're not using the unit circle right now, okay? So it would be A over C, right? Okay, now I want to look at what is cosine of pi over 2 minus theta. Okay, so cosine is the adjacent leg over the hypotenuse, right? So this pi over 2 minus theta, the adjacent leg is this A, right? And the hypotenuse is C. So this is A over C, okay? Now I want to do cosine of theta. cosine of angle theta. Okay, cosine of angle theta is the adjacent leg. So for angle theta, the adjacent leg is B over the hypotenuse, which is C. So this would be B over C. Okay, and then I want to do sine of pi over 2 minus theta. So sine of pi over 2 minus theta. So sine is the opposite leg over the hypotenuse. So for this angle right here, this is the angle we're at, right? The opposite leg is going to be B over C. Okay? Now I want to look at tan of theta, and we're going to look at all 6 trig functions for theta, okay? So tan of theta is the opposite leg over the adjacent, right? So tan of theta would be A over B, because A would be the opposite leg and B would be the adjacent leg, okay? What is cotangent of pi over 2 minus theta? Well, cotangent of pi over 2 minus theta would be, okay, if tangent is the opposite leg over the adjacent leg, cotangent would be the adjacent leg over the opposite leg. So the adjacent leg for pi over 2 minus theta is A, and the opposite leg would be B. So this would be A over B. Okay, how about cotangent of angle theta? Cotangent of angle theta would be, again, the adjacent leg over the opposite leg. So for theta, the adjacent leg is B and the opposite leg is A. So this would be B over A. Tangent of pi over 2 minus theta is equal to, okay, so tangent is the opposite leg over the adjacent leg. So for this angle pi over 2 minus theta, the opposite leg is B and the adjacent leg is A. So this one would be B over A. There's a reason these are called co-function identities. Sine, cosine, cosine, sine, tan, cotangent, cotangent, tan. I bet you know the next one we're going to do, okay? Well, maybe not specifically. The next 2 we're going to do. Okay, so secant theta. So what's secant theta? Secant theta is defined as, okay, the hypotenuse over the adjacent leg. So that would be C over B. Okay, then we're going to do cosecant. So cosecant of pi over 2 minus theta. Hopefully you're seeing something over here, okay? Cosecant pi over 2 minus theta. Cosecant pi over 2 minus theta is defined as the opposite, the hypotenuse over the opposite leg, okay? So the hypotenuse is C over the opposite leg for this pi over 2 minus theta angle would be B. So this would be C over B also, right? Okay. All right. So then the next one, cosecant theta. Okay, so cosecant theta, cosecant is the reciprocal of sine. Sine is y over r, or opposite over hypotenuse. So this is going to be hypotenuse over opposite. Okay, so hypotenuse is C. For angle theta, the opposite is A. So this would be C over A. And then we're going to do secant of pi over 2 minus theta. Okay, all right, so this is the reciprocal of cosine, right? And cosine is the adjacent leg over the hypotenuse. So this one's going to be hypotenuse over adjacent leg. So hypotenuse over adjacent leg for this one, the hypotenuse is C. The adjacent leg is A, so C over A. And you see something that happened every single time. Sine theta, cosine of pi over 2 minus theta. Cosine theta, sine of pi over 2 minus theta. And so on. These are always going to be the same, right? And that's why these are called cofunctions. These are called cofunctions because they are the same. It's just a reflection and translation, okay? So these are complementary angles. Theta and pi over 2 minus theta are called complementary angles. That's why they're called cofunctions, okay? That's what the co comes from, is the complementary, okay? Complementary angles are 2 angles that add up to 90 degrees, okay? So that means, okay, we have 6 trig identities we have, okay? So whenever we see something like this, let's say cosine of pi over 2 minus theta, that's equivalent, okay, to the cofunction of this, of angle theta. So what's the cofunction of cosine? It's sine, right? So sine of theta. So whenever we see this, we can replace it with this one, okay? So when we see this one, sine of pi over 2 minus theta, that can be replaced with cosine of angle theta. And it has to be pi over 2 minus theta, or an equivalent version of this is 90 degrees minus theta. Okay, if we're working in degrees, this would be 90 degrees minus theta, okay? So what if we have cotangent of pi over 2 minus theta? That can be replaced with tangent of the angle theta. If we have tangent of pi over 2 minus theta, that could be replaced with cotangent theta. If we have cosecant pi over 2 minus theta, that could be replaced with secant theta. And then secant of pi over 2, I just realized you guys can't see it, secant of pi over 2 minus theta would be equivalent to cosecant of angle theta. So every time you see one of these, now it has to be, it cannot be theta minus pi over 2. Okay, at least not yet. We're gonna find a way to be able to switch this. Okay, but right now we can't. Okay, so cosine of theta minus pi over 2, we don't know what that is yet. Not yet. Okay, and here's why. What do all these start with? It has to start with pi over 2 minus theta. Okay, so that's the only time we can switch them to the direct version of these, okay? So all of these, here's 6, and these are all called co-function identities. And to be honest with you, there's not one that's more important than the other, okay? So far we've learned 6 reciprocal identities, 2 quotient identities, 3 Pythagorean identities, and now 6 co-function identities. And the next thing we're going to do are called odd and even identities, okay? And there's going to be 6 of those, okay? So already we've done, so what is it? 6 and 2 make 8, and 3 make 11, and 6 more make 17. So right today we're going to do 23. There's like 40 of these, okay? But we've already done over half of them today. We'll do over half of them today, okay? All right, don't quote me on that. There's 40 of them, okay? All right, but there's gonna be a lot of these identities. And what they do is they allow us to rewrite things so that we can solve equations and do calculus, okay? So you need this for calculus, okay? It's gonna allow us to rewrite things, okay? And be able to do things, if like the way they're presented, there's no way to do it. So we gotta make these swap outs in order to do it, okay? All right. So let's go to the odd and even identity. And if you were going to break it up, this lesson up into like doing it in 2 days, and have 6 days worth of work instead of 5 days worth of work, which is fine with me. Okay. No, I have no problem with you guys doing that because I know this is a long lesson. Okay. Then what I would do is I'd probably pause it right here and then come back tomorrow and finish this up. Okay. Where you pause it doesn't really matter to me. Okay. If you want to do this over 2 days, I'm absolutely fine with that. Okay. It's about getting the work. Okay. You guys, a lot of you guys have been sending things. Oh, Mr. Mitchell, I'm so sorry for not being able to get the work done. You guys, that's not a big deal. What's a big deal is that you just get the work done. Okay. If you're a day or 2 late, it's no big deal. It's no big deal. Okay. I want to make that really clear. It's just, I need you to complete these so that if you want to take calculus, you can take calculus. Okay. Because without this stuff, it's going to make calculus really, really difficult. Okay. Because we refer to all this stuff in calculus. Okay. And I realize we're probably not going to be the best like we normally are, and that's okay. And I'll work with you when we're in calculus, okay, on going over this stuff, okay? There's a lot of stuff that I realize we're going to have to work through next year, okay, when we start meeting face to face, which I cannot wait. I can't wait. I don't like teaching this way, okay, at all. All right, I'd much rather be in front of you guys, okay? All right, so let's do these odd even identities. Okay, so for these odd and even identities, I want to look at two angles, okay, that are the same size, but the rotation's opposite, okay? So angle theta, we're going to rotate this way in a positive direction. Let's say it's 30 degrees, okay? And then we're going to also want to rotate the same angle, but in the opposite direction. So clockwise, which would be a negative rotation. And we're going to do that with a negative angle, right? So like this is 30 degrees and this one's negative 30 degrees. Okay. So if these angles are the same, this is going to hold true. Okay. So this would be my R, right? And this would be my R. Okay. And right here, I'd have to go to the right. Okay. And it would be the same X. Okay. So both of these triangles, whether it's 30 degrees, even if I rotate and I go past 90 degrees and I rotate over here, okay, and I rotate the same angle this way, right, they'd be up here and we would have the same X. So they're both these triangles are going to share the same X, whether we're right here or over here in these two quadrants. Okay. All right. So right now I know that this point right here must have this point and this point have to have the same X coordinate. Okay. Now, this one, okay, this Y right here, I know because I'm in the first quadrant, Y is going to be positive. So comma Y. Okay. Now, this wouldn't be positive Y. This would have to be negative Y because we're going down, right? So negative Y. Okay. And we're going to look at the different ratios on how to rewrite this so it's the same. Okay. All right. Even if I rotate, okay, so basically what this is saying is the Y's are going to be opposites, right? Even if I take these 2 points and rotate it and they're both, the same angle of rotation, let's say like 120 degrees, that would put this one over here, and negative 120 degrees, that would put this one over here. They would have opposite Y values. They would have the same X value, opposite Y's. What if we rotate and we go past 180 degrees, let's say 210 degrees, then this would rotate all the way over to here, 210 degrees, and this point right here would rotate all the way over to here to like 210 degrees, and it'd be up here, right? Notice for these two triangles, right, the X would be the same, but they would have opposite Y's. Okay, so that's something we're going to use to our advantage. Okay, so here we go. All right, so what is, and there's 6 of these, okay, what is sine of angle negative theta? How could I rewrite that a different way? Okay, so I want to know how this is going to be rewritten. Okay, all right, so I'm going to change this to the ratio. Okay, so sine of negative theta, so that's this one, right? And it would be my y coordinate over my r, right? So this would be negative y over r. But negative y over r is equivalent to negative y over r, right? And what's y over r? Well, y over r is the sine ratio for angle theta, but there's a negative in front, right? So that means this could be rewritten as negative sine of angle theta. Okay, so sine of negative theta is always going to be equivalent to negative sine theta. Okay, so it like sine of negative 30 degrees is equivalent to negative sine of 30 degrees. Okay, sine of negative 120 degrees is equivalent to negative sine of 120 degrees. Okay, that's what this means. Okay, cosine of negative theta. So we're going to put negative angles in all this and see what we get out. Okay, so cosine of negative theta. So that's this angle again, right? Well, cosine is be the x over the r, right? So this would be x over r. Okay, and x over r is equivalent to x over r, right? Has to be, right? And what's x over r? Well, x over r is just cosine of theta. So cosine of negative 30 degrees would be equivalent to cosine of 30 degrees. And notice no negative came out, huh? Because they're the same, all right? Because for these two triangles, the x's are going to be the same, okay? They're going to share that x, okay? And that's why it's not going to change, okay? For both of these ratios, cosine of negative theta is x over r, cosine of theta is x over r, okay? So these two have to be equal, okay? How about tan of negative theta? What is that going to be equivalent to? Well, tangent of negative theta, going from our negative angle theta, right? It would be negative y over x. So that would be equivalent to negative y over x. Well, what's y over x? Well, that's tan of theta, right? So this is equivalent to negative tan of theta. Okay? And basically it's this. Any trig ratio that deals with y, you're going to pull a negative out in front. But not when it's not doesn't deal with y. Like we didn't have to do it right here, it just switched over, right? Cosine of negative theta. We didn't need the negative, right? Okay. If that helps you, okay? So sine of negative theta is equal to negative sine theta. Cosine of negative theta is cosine theta. Tan of negative theta is equal to negative tan theta, okay? So how about cosecant of negative theta? What is that equivalent to? Is it equivalent to negative cosecant theta, or is it equivalent to cosecant theta? Okay, so cosecant of negative theta, that's the reciprocal of sine, right? So this is going to be r over negative y. R over negative y, because we're using this angle, right? The negative theta angle, okay? Well, r over negative y could be written as negative r over y. And what is r over y? Well, r over y is cosecant of angle theta with a negative in front, right? So negative cosecant of theta, okay? How about secant of negative theta? Okay, secant of negative theta would be r over x. Okay, well, r over x is still r over x, right? So r over x is secant negative theta, but it's also secant of theta. Okay? This secant of a negative angle is always going to equal secant of the positive angle, okay? Always going to be true, okay? Cotangent of negative theta. What is that one going to equal? Is it going to equal cotangent theta, or is it going to equal negative cotangent theta? Well, let's work it out, okay? So cotangent of negative theta would be x over negative y. Okay, but x over negative y could be written as negative x over y. And x over y is simply cotangent of angle theta. So this would be equal to negative cotangent of angle theta. And notice, any of the trig ratios that dealt with y, to rewrite it, we had to fix it, we had to put a negative in front of the regular angle, right? The positive angle, okay? So that was, this one had a y, this one didn't. So we didn't need to compensate with the negative, right? This tangent deals with y, right? Deals with the opposite leg, right? So we need a negative in front. Cosecant deals with y. We need a negative in front, okay, for it to be the same. Secant doesn't deal with y, right? We didn't need a negative to fix it, okay? And then cotangent, we needed a negative to replace, right? To fix it and make it equal, okay? All right, so that's it. So we've learned 23 identities today, okay? All right, and you need to know all of these 6, okay? You're gonna see these and you're gonna have to swap them out, okay? All right. Okay, so let me show you what we're gonna do with this. Now let's do some examples, okay? And then we'll be done for today. Okay, so for this first example, okay, I want to be honest with you guys. Really, these are gonna be these two I think are the hardest ones we're gonna do right now, okay? All right. So what you and it's going to be hard right now because like what do I grab and use, and what happens is you got to jump in and just start doing it and see and watch me show you like my thought process of what I'm going through. Okay, so we want to be able to find sine of angle theta and cosine of angle if we know that tan of theta is equal to 5 and we know that cosine theta has to be greater than 0. Okay, now you may be thinking, oh, tan theta, I can just switch tan theta to be sine theta over cosine theta. And you'd be right. This tan theta could be swapped out with sine theta over cosine theta, and it's equal to 5. There's a problem with that. And the problem is this. We would still have 2 unknowns there, right? And so you can only solve an equation when there's one unknown. And the problem is we don't know sine theta, and we also don't know cosine theta. Okay. I am going to use that, but not yet. Okay. So what is something else we can use? Okay. And I'm going to tell you it's the Pythagorean identity, one of the Pythagorean identities. Okay. So what I can use, because I was giving tan theta, I'm going to use this identity. So I know that 1 plus tan squared theta is equal to secant squared theta. Okay, now you may be wondering, like, why did you pick that one? Okay, so here's why. I know what tan theta is, right? Tan theta is 5. So I can put a 5 here, okay? And then the secant theta, why am I using secant theta? Well, I know secant theta could be written as 1 over cosine theta. And so what happens is this could be converted to an equation that's just one unknown, cosine theta. Okay, and I can solve it. Okay, and that's actually what we're going to do. Okay, so this is going to be 1 plus, and then tan theta is 5. So this tan squared theta means we're going to take whatever tan theta is and we're going to square it. Okay, all right, and then this is equivalent to, and secant theta can be written as 1 over cosine theta. So this would be, and you guys, I'm not gonna change the secant theta to 1 over cosine theta in parentheses and then square it. Okay, I'm just gonna those are gonna be the same thing. Okay, so this becomes 1 over cosine squared theta. Okay, all right. So what's 5 squared? Well, that's 25, right? Plus 1 is 26. So this is 26 is equal to 1 over cosine squared theta. Okay, now to clear this out, I could multiply both sides by cosine squared theta, right? And that would give me 26 cosine squared theta is equal to 1. Now I want to say there's other ways to do it. I'm actually doing this differently than I've done in years past. Okay, and I'm doing it because I think it might help you to realize I used this trig identity, right? And then I switched this one out with another trig identity, okay? And I switched the tan theta out with a number, okay? And then what I'm going to do is I'm going to divide both sides by 26. So that would give me cosine squared theta is equal to 1 over 26. Okay, now this is the answer to cosine squared theta. I want to know what cosine theta is, right? And I also want to know what sine theta is, okay? All right, so I'm going to square root both sides. This would be the absolute value of cosine theta. Okay, now I'm going to skip that part and I'm just going to go, okay, this is cosine theta is equal to plus or minus. There's two answers to this, okay? The square root of 1, which is 1, over the square root of 26, okay? Now, up here, they're telling you cosine theta has to be positive. So guess what? It can't be the negative one, okay? So now I know that cosine of theta is equal to positive 1 over the square root of 26, okay? Now, what we can do next is this, is we can, I want you to do this because this is a number. You can't simplify the square root of 26, but we can simplify 1 over the square root of 26 by multiplying by the square root of 26 over the square root of 26. And so this would be the equivalent of the square root of 26 over 26. Okay, now you know what cosine theta is. Okay, so now how do I get what sine theta is? Okay, so I know I'm going to use this trig identity. I know that tan theta is equivalent to sine of theta over cosine theta. Now, I didn't want to start with this because there was two unknowns, right? But now there's only one unknown because I know what tan theta is because it was given to me. It's 5. And I now know what cosine theta is. It's 1 over the square root of 26. So this is sine of theta over, okay, 1 over the square root of 26, or the square root of 26 over 26, right? You could actually do either one, okay? I'm going to do this one, okay? Okay, now It sure would be nice if this denominator was just 1, right? So what I'm going to do is I'm going to multiply by the square root of 26 over the square root of 26. That's 1, right? Okay, this is 1. So it's not going to change the value of this, okay? So this would be 5 is equal to the square root of 26 sine of theta, right? And this denominator would just be 1, right? So I wouldn't need this, okay? I wouldn't need the denominator because it's just 1, okay? And now I can get sine theta by itself because I can just divide both sides by the square root of 26. So that would mean sine of theta is equal to 5 over the square root of 26. Now I want you to simplify this, okay? Because that's a perfectly good answer, but it's not the best answer, okay? It is the right answer. It's not the best answer though, okay? So I'm going to multiply top and bottom by the square root of 26, and that gives me 5 square roots of 26 over 26. And that's the best answer, okay? All right, there's more than one way you could do this, okay? So I want to make that really clear. And that's the beauty of this is as long as you do things correctly, okay, you may do things differently than I do, but you can still get the same answer, okay? So you definitely have to use the 1 plus tan squared theta is equal to secant squared theta. Now, some of you might leave this as secant squared theta and solve for secant theta and then just do the reciprocal, okay? And that would be fine because then you'd have cosine theta, okay? Some of you right here might not use 1 over the square root of 26. Some of you might use square root of 26 over 26, and that would be absolutely fine, okay? So that's just different things that you did that were slightly differently than I did, and it would be okay. Okay, I want to make that really clear. It's okay to do things a little bit differently than I did. All of us at the end, as long as you do everything right, will come up with the same exact answer to these, okay? So, all right? Okay. All right, so here we go. Let's go with the next one. Example number 2. This one is probably going to be the hardest one, okay? All right, so some of you might recognize this, but you'd be wrong, okay? This isn't a co-function identity yet. It's not a co-function identity yet, okay? Because it would be, we could do a co-function identity if it was pi over 2 minus theta, but it's not. It's theta minus pi over 2. So there's got to be a way we can rewrite this, okay? And there is. And let me show you how we're going to do this, okay? So this means sine of theta minus pi over 2. Okay, because these are the wrong signs, right? They're opposite signs. I sure would like it if it was pi over 2 minus theta. I can actually force that to happen, okay? But the way I'm going to do that is I'm going to factor a negative out of both of these, okay? Now, if this is positive right now, if I factor out a negative, I'm going to be left with a negative, okay? So this is sine of negative parenthesis. This pi over 2 is going to become positive, and the theta is going to become negative, okay? And then I'm going to rewrite it so it's pi over 2 minus theta. Anytime you factor a negative out of something, it's going to change all the signs, right? So this is going to be negative, and this one's now going to be positive, okay? All right. Everybody okay with that? I wish I could hear you. Okay. All right. The next thing we can do is to go to the next thing. This is sine of a negative angle, right? That's an even odd identity, okay? So sine of a negative angle is equivalent to negative sine of that angle, okay? And the angle that I'm talking about is this pi over 2 minus theta. That's an angle, okay? All right, so that means this could be rewritten as negative, okay, sine of pi over 2 minus theta. These are equivalent, okay? And what I did to go from here to here is I used this identity. I knew that if I took sine of any angle that's negative, that's always going to be equivalent to negative sine of theta. Okay, so I realized, like, you may be confused, like, there's theta here, right? And there's theta here, right? But it's negative of the angle, whatever this angle is, right? This pi over 2 minus theta is an angle, right? And I'm taking the negative of that angle. Okay, so you got to think of this as being like your theta right here, okay? This whole thing right here is being like your theta. which means you can take this negative and pull it out, right? In fact, and it doesn't really get factored out. It's just an equivalent way of writing it, okay? So this negative came out here, okay? And I want you to realize that, okay? Why did I want to do that? Because this is going to allow me, okay, to use a cofunction identity now. Because now if you look, and don't worry about this negative, but just this is a cofunction identity now, okay? And sine of pi over 2 minus theta is equivalent to cosine of this angle theta. Okay, now the negative just comes along with us, okay? So we're swapping this out with negative, and then we're swapping the sine of pi over 2 minus theta out with cosine of theta. Okay, so now how do we go from here to here? We use this identity, that sine of pi over 2 minus theta is always going to be equivalent to cosine of theta. Okay, so why did I care about even doing that? It's because I was given cosine of theta, right? Cosine of theta is equal to negative 0.34. Okay, so that's going to allow me now, because now I know cosine. This cosine theta right here, I know is the number negative 0.34. They're the same thing. So that's going to allow me to swap this out, this cosine theta. It's not going to allow me to switch out the negative, but it's going to allow me to switch out the cosine theta with negative 0.34. So this is equivalent to negative of negative 0.34. And negative times a negative is a positive. So this is equal to 0.34. And we figured out what this is equal to. So sine of theta minus pi over 2 is equivalent to 0.34. Okay? And we use two identities here. Okay? All right? Okay, so let's go to example number 3. So example number 3 says simplify sine cubed x plus sine x cosine squared x, and then support your answer graphically. We're not going to be able to support our answer graphically because you need graphing calculator. I mean, you could use Desmos, but we're not going to be able to do that part of it for this, okay? So if I want to simplify this, okay, I want to know what this is equivalent to. Okay, so sine cubed x plus sine of x cosine squared x. Okay, what does sine cubed x mean? Okay, so when you see this, what does it mean? It really means sine x times sine x times sine x. 3 of them in a row, sine x times sine x times sine x, okay? Okay, so what that means is I could break this up. This is really sine of x times sine squared x, and I'm using exponent rules there too, right? Because if I'm multiplying them, right, and I'm squaring, and this is a power of 1, then when I multiply them, that would be a power of 3, okay? And then plus sine of x cosine squared of x. Okay, so how's this beneficial? Why am I rewriting it like this? Because I notice there's a sine x here and there's a sine x in this one, right? Which means I can factor it out. So this is equivalent to sine of x, which I'm going to factor out, times what's left behind. Well, out of this, I factor out this sine x, right? And I'm left with sine squared x plus, and this sine x got factored out, right? And I'm left with plus cosine squared x. You should recognize that. Sine squared x plus cosine squared x. That's a Pythagorean identity, right? It doesn't have to be cosine that's first, right? But because order, when we add in, order doesn't matter, okay? So this means, okay, sine of x, I'm going to go ahead and write it in the correct order, okay? Order doesn't matter when you're adding, right? So this is equivalent to cosine squared x plus sine squared x. Well, what do we know this is? Well, that's equivalent to the number 1. So this is equal to sine of x times 1. Well, what's sine x times 1? Just sine x. So this ugly thing that looked like it's horrendous, right? Sine cubed x plus sine x cosine times cosine squared x is simply the same as sine of x. They're the same thing. If you graph this, and that's why they say support your answer graphically, if you graph this and you graph this, they're the same graph. They are identical, okay? That's why these are called identities, because they're identical, okay? These two things are identical. So like in calculus, okay, we have to do calculus on this. Well, would you rather do calculus on this, or would you rather do calculus on something simple? Something simple, right? And that's why we're learning this, okay? Okay. So we're in calculus, we're gonna have to take this and switch it to something like this to make it easier for us. Okay. All right, let's go to example. Okay, I really like these. These, you know what you're going to get out. You're either going to get the number 1 out or the number -1 out, okay? After we're all said and done, okay? Okay, so we're going to start with this. Cotangent of -x times tan of -x, okay? So cotangent of -x times tan of -x. Okay, so for this one, we're going to use an odd even identity because now theta has been replaced with x here, okay? That doesn't matter, okay? This x is the angle of rotation, okay? All right, so cotangent of -x, that's an odd even identity. That's the same as negative cotangent of x. So I'm going to replace cotangent of -x with negative cotangent of x, okay? Tan of -x. And that's where it's helpful. Like I have these memorized, okay? It's helpful to have you memorize. Like you may not be able to come up with them as fast as I am right now, right? And it's because they're not fresh, they're not in your memory, right? You don't have a working memory to use and go, oh, it's this, okay? That's why it's helpful to have them memorized, because then you can see stuff. Where if you don't have it memorized, you will never see it, okay? You'd have to always refer back to stuff, okay? And try to find it, and you don't even know where to look, okay? So that's why it's powerful if you commit these to memory, okay? Okay, so tan of -x is also an odd even identity. Okay, so tan of -x can be written as negative tan of x. Okay, and I used this identity I used these two identities for this. I did cotangent of negative theta is equal to negative cotangent of theta. And I also use tan of negative theta is equal to negative tan of theta. Okay, so now I'm just going to do some math. What happens when we multiply a negative times a negative? It becomes a positive, right? So that makes this equivalent to cotangent of x tangent of x. And when you write, we don't have to put the dot here, but we're actually multiplying these, right? Okay, so where do we go from here? Okay, so now again, it's useful to know to have it working memory, okay? Cotangent theta can be rewritten as cosine x over sine of angle x. So this can be written as cosine of x over sine of x times tangent of x. Well, tangent of x could be written as sine of x over cosine of x. And the two identities that I used was cotangent theta is equal to cosine theta over sine theta. And I also used tan theta is equal to sine theta over cosine theta, right? Okay, so in essence, what we have is two fractions that we're multiplying together, right? Well, how do you multiply fractions together? You multiply the numerators together and the denominators together, right? So if I multiply these together, right, could I rearrange this? Can you rearrange multiplication? Yes. So I actually could rearrange this denominator multiplication or the numerator, it doesn't really matter, okay? And rewrite this as cosine of x over cosine of x times sine of x over sine of x. So I just rearranged the order that we were multiplying them in the denominator, right? And you can do that because you still have the same thing, right? Okay, so cosine x times sine x over cosine x and you look at this, wait, the numerator and the denominator are exactly the same, right? That means it has to be 1, right? So this is equal to 1. And we knew we were either going to get 1 or -1 out, okay? Now, some of you might have said, oh, wait, I did that up here, right? I made cosine x over cosine x equal to 1 times 1, right? And 1 times 1 is 1. That would be fine. That'd just be another way of doing it, okay? All right, let's go to example number 5 now, guys. Okay, so we're going to simplify this by expanding it first, okay? So we're going to, and expanding means multiplying it out, okay? So we want to simplify the expression secant x plus 1 times secant x minus 1 over sine squared x, okay? So we're going to start by writing that, okay? That's what you should start with, secant x plus 1 times secant x minus 1, because you're trying to tell me what this is the same as, okay? Over sine squared x. Okay, so secant x plus 1 times secant x plus 1, okay? So we can use an area model to multiply that out, okay? So we're going to write equals. Some of you I know can do it in your head, okay? You know, I'm going to show you how to do it without the area model, okay? So to multiply it out without the area model, we're going to take secant x and multiply it by secant x. So we're going to take this first term and distribute it. And then we're going to move over to the next term and distribute that, okay? It's a lot faster than the area model to multiply, okay? So secant x times secant x would be secant squared x. And then secant x times -1, that'd be negative secant x. And then positive 1 times secant x is plus 1 secant x. And then positive 1 times -1, and that'd be -1 over sine squared x. Okay, so what does this become? Okay, so I have a secant x and a minus secant x and plus 1 secant x, right? These cancel each other out, and you're left with secant squared x minus 1 over sine squared x. Okay, so now where can we go from here, right? Where can we go from here? I see some squares, right? Some squared trig functions. So automatically when you see squared trig functions, we should be thinking, Pythagorean identity, right? Okay. So we know one of the Pythagorean identities is cosine squared theta plus sine squared theta is equal to 1. Okay, how do you get secant squared theta, right? You get secant squared theta, okay, by 1 over cosine squared theta, okay? So this is a Pythagorean identity I know, right? If I divide each of these by cosine squared theta, right, this is going to give me a secant squared theta when I divide this 1 by cosine squared theta, okay? So what happens when you divide cosine squared theta by cosine squared theta? You get 1 plus. What happens when you take sine squared theta divided by cosine squared theta? You get tan squared theta. What happens when you take 1 and divide it by cosine squared theta? You get secant squared theta. Can I manipulate this and get this one? And you can by moving this 1 over, right? So I know that tan squared theta is equal to secant squared theta minus 1. Okay, how does that help me? That means this top becomes tan squared theta, okay? Because that's an identity that must be true, okay? Because it came from this Pythagorean identity, which came from this one, okay? Okay, so that numerator can be rewritten as tan squared theta over sine squared theta. Okay, we want this, and I should have said this at the very beginning, we want to simplify this down to either a constant or a basic trig function. So it's going to come down to one trig function or a number, okay? So right now, what do we have this as? Okay, we have tan squared theta over sine squared theta. That's two basic trig functions, right? We want one of them, okay? So tan squared theta, I'm going to use a quotient identity, okay? This is my main fraction bar. So tan squared theta can be replaced with sine squared theta over cosine squared theta. Sine squared theta over cosine squared theta is the same as tan squared theta over sine squared theta. But now I have a complex fraction, right? Because I have in the numerator, I have a denominator of cosine squared theta. Well, what I'm going to do is I'm going to multiply by cosine squared theta over cosine squared theta. What is cosine squared theta over cosine squared theta? That's 1, right? But when I multiply this numerator with this numerator, I'm going to get sine squared theta. I'm going to slide it up for you guys to see. And this denominator becomes sine squared theta cosine squared theta. And this could be written as sine squared theta over, this came from multiplying fractions together, okay? So sine squared theta over sine squared theta times 1 over cosine squared theta. And what happens to your sine squared thetas? They become a 1. Okay, so this becomes 1 times 1 over cosine squared theta, right? So this is 1 over cosine squared theta. Now, some of you might have looked at this and gone, wait, Mr. Mitchell, because the numerator is a product and the denominator is a product, I could have gone, right? And canceled, right? Like remember this sound effect? That's the sound effect of canceling, right? So this and this one could cancel and make a 1, right? And you'd be left with 1 over cosine squared theta. Just I would love it if you did that, but I know a lot of people don't understand when you can cross these out and when you can't. The reason we can cross these out is because we can rewrite it this way, okay? But what is 1 over cosine squared theta? That's really secant squared theta. So this becomes down to secant squared theta. And we've gotten it down to a basic trig function. It's just secant squared theta. Okay, now could there be other ways you did this? Yes, absolutely. Okay, so let me say this right here, we could have switched this right here, the secant squared theta, to 1 over cosine squared theta. So we could have done that. You could have done it that way, okay? 1 over cosine squared theta. And then you would have had a complex fraction that you would have had to clear out. And there's other ways. So I just want to make that really clear. There's other ways than the way I did it on this to do this, okay? And it would be absolutely correct if you did it, okay? As long as you did everything correct and we wound up with the same answer, okay? As long as you did mathematically things that were correct, that were true, okay, we will get the same answer, okay? Even though you may have seen something different than me, okay? All right, let's go to example 6, and that'll be our last. Okay, so I want to take this trig expression, secant squared x cosecant x over secant squared x plus cosecant squared x, and to one involving only sines and cosines, and then I want to simplify it to a basic trig function. Okay, so I'm telling you how to do it, okay? You want to switch everything to sines and cosines, okay? And then we're going to clean it up and see what we have left, okay? So you have to start with what we're trying to simplify, okay? And with a chain of equals, okay, you're going to show that it's equal to something else, okay? So secant squared x cosecant x over secant squared x plus cosecant squared x. Okay, I want to make this really clear. These secant x's do not cancel because this is a sum down here. Now, if this was a product, they would, okay? And actually one of these cosecants would cancel too, but this is a sum, not a product, right? So we can't cancel. We can't do that, all right? Okay, so I want you to switch everything to sines and cosines. Okay, so this secant squared x can be rewritten as 1 over cosine squared x. So I'm going to make a big fraction bar, okay, and this first one's going to be 1 over cosine squared x. Because secant x and 1 over cosine x are the same, okay? And then cosecant x, that's 1 over sine x. Extend my fraction bar a little bit. Okay, secant squared x here is 1 over cosine squared x. You wouldn't need the parentheses here, okay? Plus And then cosecant squared x is 1 over sine squared x. And since I put it in the first one, I'll put it in the next one too. You wouldn't have to have parentheses here either. Okay, complex fraction, right? So we have a denominator of cosine squared x here. We have a denominator of cosine squared x here. We have a denominator of sine x, and we have a denominator of sine squared x. So what I want to multiply top and bottom by is cosine squared x times sine squared x, because a sine squared x will take care of a sine squared x, and it will also at the same time take care of the sine x, okay? So I'm going to multiply by cosine squared x sine squared x over cosine squared x sine squared x. Okay, so this is two fractions being multiplied. These are two fractions that we're adding, right? We're going to do them differently, okay? So this becomes one fraction, and it'd be 1 over cosine squared x sine x. Multiply that fraction, that one fraction, with this, right? And what we would have is cosine squared x times sine squared x over cosine squared x sine x. Big main fraction bar. Now this is the sum of two things, right? So I'm going to need to distribute this with each of these fractions. So this becomes cosine squared x sine squared x over cosine squared x. Plus, and then cosine squared x sine squared x over sine squared x. Extend my main fraction bar a little bit there. Okay, what happens on this fraction? Well, the cosine squared x's cancel. This sine x cancels with one of these, so this becomes just simply sine x. The numerator is going to become sine x. And I want to move my equals, okay? I don't like it way being up here with the numerator. It really should be right here with the main fraction bar, okay? And so this becomes just sine x. And I'm going to put an equals here. There's my main fraction bar. Here, my cosine squared x's cancel, and I'm left with sine squared x, right? Here, my sine squared x's cancel, and I'm left with plus cosine squared x. Well, where do we go from here, right? Well, cosine squared x plus sine squared x. That's a Pythagorean identity, right? Whenever you see cosine squared x plus sine squared x, or sine squared x plus cosine squared x, because the order doesn't matter there, this is the same as 1. So this is equivalent to sine of x over 1, which is simply sine x. What happens a lot of times is you don't know how to get started, so you just got to jump in, and then all of a sudden, people think, oh, I have to know that this is going to happen right at the very beginning. From up here, I knew we were going to get this. No, okay, you don't know what you're going to get. Okay, you're just working your way through, and then pretty soon it starts to appear. Okay, like even here, you may not have seen it, right? Okay. And then at this point you go, oh, this is 1. Oh, it's going to be sine x. And it's kind of like that aha moment. Okay. All right. So we're going to do a lot of these, okay, over the next 10 days. Okay. For the rest of the school year. Okay. We're going to be working on stuff like this. Okay. All right, guys, that's it for today. Let me get the assignment sheet, and I'll tell you the assignment. So today what I want you to do is we did the fundamental trig identities. There's 23 of them, okay? And then I want you to do worksheet TEI-2, okay, today. And again, if you wanted to split this over 2 days, maybe do the notes one day and do the homework the next day, because I know the notes are long today, okay? And I'm going to be honest with you. This whole unit, the notes are probably going to be a little bit longer than normal, okay? A little bit, okay? Today's probably the worst, okay? Because we had to go through 23 different identities just to do some problems here. Okay, guys, hope you're kind of having fun doing these, all right? You guys take care, and I will see you tomorrow.